Now in this lecture we are going to focus on physical vapor deposition process. So physical vapor deposition process. So we can call it in short form as a PVD process. So mostly all surface treatment process are conducted under vacuum. So it means that the process in this process the pressure is lower than the atmospheric pressure. So the main reason for doing this is to increase the mean free path represented by lambda, which is a distance traveled by any molecule between two subsequent collision. So this is one molecule here, and there is another molecule. So the distance traveled between two successive collisions collide. So in gas, we have molecules moving freely in random direction with high velocity, and then they collide continuously with the others. Now, the average distance between two collisions is measured by mean free path. According to the kinetic theory of gases, the expression for mean free path is given by this expression, that is kT upon under root 2, this is under 2 sigma p. So which is proportional to the reciprocal of the gas density. That is, if the gas is denser, then the probability of collision will be higher. So the length is short. Here, K is the Boltzmann constant. T is the absolute temperature of the gas. Sigma is the cross section for the collision, which we are going to discuss just a few minutes after this. Cross section for the collision, and here P is the gas pressure. So according to the state of ideal gases, P by kT is the molecular density of our gas. So kT by P is the reciprocal of the density, that is 1 by rho. So the larger the density, then shorter the mean free path. Now sigma is the cross section for the collision. Cross section from the dimensional point of view is the area, which means we associate an area to each particle. In the equation here, we can see this under root 2 here. So here, this under root 2 is included to consider the relative velocity of our particles because they are moving in different directions. Now let's talk about the cross section of the collision, which I told you that we are going to discuss later. So now let's discuss about the cross section of the collision. So this orange circle represents the single particle and atom or molecules and our gas. So in this picture we have two molecules or atoms. We associate these red circles which represent the volume of the electron cloud. So this orange circle represents the volume of the electron cloud along the nucleus of these particles or the center of this particle. So this is the volume occupied by these particles. So they can be regarded as the collection of rigid spheres. So this is the cross section for the collision sigma. So we say that when the other particle will fall inside this cross section of the first particle, then we have collision between these two particles. So cross section is able to define the probability of the interaction between these two particles. Now, if we have a large cross section, then it means that probability of the second particle to hit this area is larger. Then we have more frequent collision and shorter mean-free path. The extension of cross section is related to specific collision we are considering. The most common one is the molecular scattering. We have simply an exchange of the momentum between two molecules with a variation of their original trajectory. In this kind of interaction, the distance which is able to produce the transfer is comparable to the radius of each particle. So in the above case of scattering, the cross section is generally a circle with radius equal to the diameter of the particle. That is the radius of the particle 1, radius of particle 1 plus radius of particle 2. So for scattering, the cross section sigma is particularly related to the particle diameter. It's related to the particle diameter. But if we consider another interaction, for example, electrostatic interaction between the ions and the neutral atom, ion typically having the positive charge interact with the electron cloud of the neutral atom. So in this case, electrostatic attraction extend over a longer range. For this kind of interaction, we can have a large cross section which results higher probability of interaction. So we have a cross section for each collisional process. For scattering, this cross section is roughly related to the particle diameter. For other interaction, we are not sure. It can depend on the range of their specific process. Now, if we consider the molecular scattering, the general conclusion is that at reduced pressure below 10⁻³ millibar, we have mean free path in the range of many centimeters. So it is comparable to the chamber size, that is to the typical distance between the elements of our chamber. So if we are able to reduce the pressure below 10 power minus 3 millibar, we can have molecules in our system which moves without collision with other molecules. So it will be a sort of ballistic trajectory for all molecules, provided that we are able to reduce the pressure in this range. We know that the atmospheric pressure is roughly 1 bar, and we are speaking to reduce the pressure below 6th order magnitude of the atmospheric pressure, which is not an easy task. So according to this interaction, we can differentiate two main flow regimes, and that is molecular flow and viscous flow. And now let's discuss about molecular flow and viscous flow, or we can discuss in this lecture itself. So there are two types of viscous flow. First one is molecular flow. Two types of flow regimes. We have two types of flow regimes. So first one is molecular flow, and second one is viscous flow. So in molecular flow, the main distance, that is mean free path, is larger compared to the characteristic size of the system. We need very low pressure and hence very low gas density. Now coming to the viscous flow, the mean free path is much shorter than the size of our system. So this flow can be either laminar or turbulent depending on the gas velocity. So in viscous flow, we can have mean free path in the range of micrometer. Now let's understand the flow condition in the first region, that is in molecular flow, which is completely different because we have very long mean free path. So we can predict the flow regimes with the help of Knudsen number, which is represented by here this number, and it's represented by lambda by this thing. Here lambda is the mean free path, and here dc is the characteristics dimension of system. Now, for example, in PVD process, the characteristic distance is the distance between the source and the substrate. Atoms are emitted from the source, and suppose this is the source, and this is the substrate. Atoms are emitted from the source and they move towards the substrate. So they travel along this distance, which can be some centimeter in the vacuum chamber. So when Knudsen number is more than 1, then molecular flow will occur. And because we have the mean free path is greater than the characteristic length of the system, so no collision will occur. In the intermediate flow, we have low value of Knudsen number, that is which ranges from 0.01, okay, and it's less than 1. So this is the intermediate flow. We have some probabilities for collision between the molecules when Knudsen number is less than 0.01. So the flow regime is viscous, and we have very frequent collision between the molecules. So in this region, we have some sort of continuity which constitutes the fluid motion. Now, just to have more practical evaluation, if we use our expression of mean free path, we can consider a gas at a room temperature which is around 300 Kelvin, and we select air as a gas where we have some specific value of sigma. So we are going to get the mean free path by this expression. This is P should be in millibar. So this is the expression which can be used for finding the mean free path. Now, if we use the pressure below 10 power minus 3 millibar, now if we are going to use the pressure below 10 power minus 3 millibar, then we have larger value of the mean free path, which is greater than 6 centimeter. So the flow regime may differ in various parts of the same system. That is, molecular flow will occur in the high vacuum chamber, but the gas flow viscously in piping near the exhaust pumps. So our vacuum system is very complex, and we have different regimes in different parts. So we don't expect molecular flow everywhere. In the next lecture, we are going to discuss about the vacuum production system. So for now, thank you.